What is a numerical integrator? Well, according to Wikipedia, a numerical integrator is an algorithm for calculating the numerical value of a definite integral. In other terms, a numerical integrator is an algorithm that solves differential equations by advancing forward in time in discrete steps, approximating solutions that may or may not have analytical formulas. This can be very useful for things like n-body simulation, since there's almost never a set of equations for the motion of the bodies, and the curve varies wildly from even the slightest change to its orbital parameters, which makes figuring out just regular integrals really difficult, which is why we use numerical integrators. There are many different types of numerical integrators, so let's look at a few. And actually, before we do, we need to discuss two important pieces of info about numerical integrators. They have an order, and they can either be symplectic or non-symplectic. Order determines the method's accuracy. The higher the order, the less error it'll have. Error can be local or global, with local error being between time steps and global error being the whole simulation. Delta t in the equations you're seeing being the time step of the simulation, which is pretty much how far the method goes forward in time. Then we have whether or not it's symplectic or not, which determines, well, I said that wrong. We're going to ignore that. Which determines whether or not it maintains the Hamiltonian structure of the system, which just means, does it maintain energy? Now that we got that out of the way, let's discuss a few methods. Starting off, we have explicit Euler, which is a first-order, non-symplectic method. It's super simple and easy to program, and very efficient, so it's commonly used in large applications that require its efficiency or speed. But it generally sucks a lot for accuracy, and it can very easily get massive amounts of error if your time step is too large, or if the system runs for a while. So, for most use cases, it ain't gonna work. So let's move on to a much more useful one, that being the numerical integrator that is velocity-Verlet. Velocity-Verlet is a second-order symplectic method, and it's not too much more complicated than explicit Euler, and it's surprisingly much more stable and less error-prone, which we'll get to see soon when I test these methods. These facts make it a very good choice for scenarios and systems that require precise energy conservation, like orbital mechanics or molecular dynamics. For our last integrator, we'll look at Runge-Kutta-4, also known as RK4, which is a well-known numerical integrator in the computer science community due to its usefulness. RK4 is a fourth-order, non-symplectic method and is the most common one so far. Not common, complicated one so far. It basically works by taking 4 precise steps into the future, records that data, and then uses said data to make a very accurate guess on the actual curve. It's unbelievably accurate, and it's really good for general purpose solving of ordinary differential equations, which is the solving that I was discussing earlier. Now that we've seen some methods, let's see how they perform. And I have the plot right here. This graph shows a gravitational simulation of the Sun-Earth-Moon system at a time step of 10 seconds, or a delta t of 10. That lasted for about 5 years. 5 years simulation time. To no surprise, Euler sucks, as you can see. It blows up, and it's nearing an error drift that is quite high, which is not good. Strangely, we can see a green line at the bottom of the graph, and if you were paying attention to the animation, you saw a blue line there as well. It seems that velocity-Verlet and RK4 are flatlining at 10 to the negative 8% error drift. If we zoom in, and there we go, we can see the insanity that is that graph. We can see that sometimes velocity-Verlet and RK4 are dropping down to 10 to the negative 13, and they're pretty equal. And it just shows the power of being symplectic or just having a high method. RK4 is conserving energy pretty well because of how accurate it is, whilst velocity-Verlet, which was built to maintain energy whilst not being as accurate, is keeping up pretty well. But it just shows that it's quite close to machine limits as well, because I was using doubles for the simulation, which go up to like 15 digits. So this is getting really close to machine limits. So that's pretty cool. And yeah, that's my short video on numerical integrators. That's pretty much all I wanted to talk about for integrators, and I want to announce something. I plan on streaming today, like when this video comes up, assuming it should come up today. I might stream in a few days. I don't know. You'll see it on my channel if you check it out. But I'm pretty much working on a C++ project for Kerbal Space Program that uses n-body simulations and this type of math, like these integrators, along with other physics systems and programming systems, to make a realistic celestial body generator. It'll pretty much be it'll make it easier to make your own custom planets in Kerbal Space Program and have them be very realistic. I plan on I should be streaming today, hopefully. I might put out like a short to advertise it as well. I don't know. And I hope you come and join me to assist me in this crappy attempt to make a program that is far above my skill level. In fact, the simulation that you saw, the thing I did, was the gravitational simulation with the plot. I got that data by using what I have so far in the program. So that's pretty cool. Thanks for watching and have a great day. See ya.